Hello everybody. In today's video I will be covering 1D kinematics in AP Physics, how it is covered in there. So this is the first unit of the course. It is, I believe, the easiest unit. However, it gives you a very good fundamental idea of what you're going to be doing in this class, as it shows you working with the equations, manipulating equations, and just getting an understanding for physics as it is. It is personally one of my favorite units and really made me enjoy physics a lot more. So I'm going to start by listing off all the equations. So we have, I'm just going to write on the side what everything means. So delta x equals is change in displacement or change in position, or displacement. So I say or, but those are the same. Change in position is displacement. I just added the or as a different way to refer to it. Then we have VI is the initial velocity. Then we have VF is the final velocity. Then we have A is the acceleration. So, to really understand what velocity is, I'll write down the equation. So we have V average, the average velocity, is equal to distance traveled divided by the time that it takes. So for something with constant velocity, distance divided by time will be constant throughout the entire existence of its movement. So there will be no net acceleration and no change in velocity. The second equation you need to know is A. This is also average A, but we will not work with problems that have a change in acceleration, so this part isn't really necessary. So A equals VF minus VI over T, which is also equal to delta V over T. And then this should be rewritten as delta x over t. So velocity is to position what acceleration is to velocity. Acceleration is the rate of change of velocity. So, and this should also be delta t's, all these. So if you remember from Algebra 1, we had a line has the format y equals mx plus b, where m, the slope of the line, was delta y over delta x. So what this means is that acceleration is the slope of a velocity versus time graph. So let's say we have a v versus t graph. Let's say the slope of this line is 2, then a equals 2, so delta v over delta t equals 2. And the same applies to velocity when it comes to a position versus time graph, where the slope of this graph is equal to change in x over change in time, which is equal to the slope. So for our next equation, we relate the difference in distance to the initial velocity and the acceleration of the object. So this equation really shows you how far something travels when you know its initial velocity and you know its acceleration. That's when you could use this equation. This equation does require time, however. So if we are not given time in our directions, then we could use the last equation that we'll be going over, which is VF squared equals VI squared plus 2A delta x. So this equation relates the final velocity, the initial velocity, the acceleration, and the distance traveled. So how do we derive these last two equations? So for this equation, delta x equals VIT plus 1 over 2AT squared. We can look at the graph and the area under the graph of an acceleration versus time graph. A versus T. So assuming constant acceleration, let's say that the acceleration is a number c, we will have a straight line going through the graph of quantity c. So let's say at any given time we want to see the average, we want to see how far it's what the velocity is. So from our equation, A equals delta V over T. We can multiply both sides by T. And we get AT equals delta V. So by multiplying, aka looking at the area under the graph from point TO of this graph, we get C times delta T, so we'll just call this delta T, equals velocity. So V equals C delta T. Now, for our velocity versus time graph, we see that this area increases at a constant rate. It's not growing exponentially because every time you move a little bit t, you get a certain amount, which is c times that little move in t. And you can see right here of extra velocity. So when we look at our velocity versus time graph, we can see that it will have this form, just a straight line. Now this straight line is equal to c times delta t, where c is the acceleration. So I will actually just rewrite this as a equals c, and then I will just write this as an a. So this is just equal to a times delta t. Now, since we have v equals delta x over t, we can see that v times t equals delta x. So by looking at the area under this graph, we can tell how far our position has changed at each different time given by the area under this function. So this line is a triangle, and the equation for area of a triangle is A equals 1/2 base times height. Now the base of this triangle is delta t. So A equals 1 over 2 delta t. And then the height of our triangle is just equal to this this factor, a times delta t, where delta t is once again measured in these little differences in t. So a times delta t. So our area, we also know, is equal to delta x, because vt equals delta x, and we are currently looking at this. So we have delta x equals 1 over 2, and then 2 delta x's. So this is a, and then times t. squared, since there are two delta x's. So this term of plus VIT is assuming that we have an initial velocity such that it starts at a different point. So let's say it starts at a point VI. Then we would just have to add VI times t, since this would, I'll rewrite this in a new graph. VT. Let's say we start at point VI. This has a t. This is the slope of the graph. Then we have this area underneath is equal to VI times t. So we have to add that in to our equation. So we have delta x equals 1/2 AT squared plus VI times t. That is our equation. Now the second equation we can get two different ways. I will be showing you the energy derivation for this equation. So let's go. Let's say that you have an object which has an initial velocity of VI and is in an initial position h above the ground. So given that, you know that E equals 1/2 mv squared plus mgh, since this is our equation for energy. You will learn this later in the year. I'm just showing you how it is derived right now using the principle of conservation of energy. So we have E1 equals 1/2 mv squared plus mgh. And then let's say later it is observed to have V2. I don't know why this is doing this. Cover over that. So let's say this has a velocity V2, which is smaller, a height H2, which is larger. Then we have E2 equals 1/2 mv2 squared plus mgh2. So we know for a conservation of energy that E1 equals E2. And then we could set these two equations equal to each other, since we know that this side of the equation must be equal to each other. So we get 1/2 mv1 squared plus mgh1 equals 1/2 mv2 squared plus mgh2. If we divide our whole equation by m, wow, this is very bad, m, then we get 1/2 vi squared plus gh equals 1/2 v2 squared plus gh2. Now h1 minus h2 is equal to delta x, which is in our equation. So we are going to want to get, also I'll rewrite this as vf squared instead of v2 squared. So we will be solving for vf. So let's go about by multiplying both sides by 2. Then we get vi squared plus 2gh1 equals vf squared plus gh2. 2gh2, sorry. So then we subtract 2gh2 from both sides, and we get vi squared plus 2gh1 minus 2gh2. We could factor out the gh, and we get vi squared plus, I'll put vf over here, vf squared equals vi squared plus 2g times h1 minus h2 and that h1 minus h2 is equal to our delta x, our change in position. So we have vf squared equals vi squared plus 2 times g, which is acceleration due to gravity, times delta x. There is our second equation. So let's move somewhere else on the page for our next part. Now, let's look at some graphs. Let's say I give you a graph of d versus t, and this is the graph, a straight line. Now, which of the following statements are true? So, one is that this graph is or has acceleration. Now, the second is this, has non-zero. I'll write that. This graph has a velocity greater that is constant, and the third is that v equals 0 and a is equal to some constant c, which is where c is greater than 0, or the absolute value of c is greater than 0. Now, take a minute and think of which of these answers are true. Now, the answer is that none of these are actually true unless, oh wait, never mind, sorry about that. The answer is that number 2 is true. I meant to give you a trick question and I accidentally did not. So this graph has a velocity that is constant. So we know this because the velocity is equal to the slope of a d versus t graph. And at the beginning, I told you that this slope is constant. Now, for our second question, I will give you this graph. Imagine it's just a straight line. Now, which of the following are true? 1, a equals 0. 2, the absolute value of a is greater than 0. 3, dude, I don't know why this does this. Sorry about that. 3, v is constant, and 4, is that the object is at rest. So more than one of these can be true, by the way. This can be a question that has multiple right answers. So take a minute and pause and think through this for yourself. Now, if you said that answer choice 2 is correct, you would be correct. This graph has a greater than 0 acceleration, since we know that acceleration is equal to delta v over delta t, which is equal to the slope of a velocity versus time graph. Now, I will give you one more question. Here, I'll look for some space somewhere. I'll give you one more question and try your best to get this one right. And let me know in the comments if you understand this and if you like this type of video, because I like teaching this type of stuff. I find it very interesting. So, this is our final problem. Sorry about that. Now, the first option is that sorry, that looks a bit weird. The absolute value of A is equal to 0. The second option is V is constant. Third option is A is greater than the absolute value of, the absolute value of A is greater than 0. So the object has an acceleration. And the fourth option, sorry, delta x across any point t is equal to 0. Now, take a minute, pause the video, and let me know which option you think is correct. And 3, 2, 1, the answer is that the object is accelerating. Now, we do not know if A is constant, since if this was, let's say, f of t equals x cubed, then the acceleration would be equal to the second derivative, which you do not need to know this, which, let's say this is x of t, which would be equal to a function of time, which would actually just be 6x. So the acceleration would be changing. So it might not be constant acceleration. We do not know. So here are the notes from today. A lot of work here, a lot of stuff done. I hope you guys learned a lot and enjoyed the video. Thank you for watching and have a great rest of your day. Thank you.